All right, in this section, we're going to discuss reaction rates in more detail. Reaction rates can be determined by monitoring the change in concentration of either the reactants or the products as a function of time. So in the image here, in red, we have our reactants at time 0 seconds. We have 1 mole of A, which is our reactants. And we measure along at various times. At 20 seconds, at 40 seconds, we see we have 0.5 moles of A reactant, 0.5 moles of B product. And then after 40 seconds, we have 0.25 moles of A and 0.75 moles of B. So we're just monitoring the experiment as it moves forward as reactants become products. All right, so let's look at some experimental data. These data were collected by measuring the concentration of C4H9Cl. And if we look at our reactions, C4H9Cl, aqueous, is one of our reactants. So it was measured versus time, so the concentration versus time, from its initiation at time equals 0 until all of the reactant was consumed. We'll analyze the data on the next slide to determine the rate of change of concentration versus time. But just take a look at this. Every 50 seconds, this is our time, every 50 seconds, we took a concentration measurement for the C4H9Cl reactant. These square brackets here represent concentration as molarity, or the moles of C4H9Cl per liter. That's our concentration, moles per liter of the solution. So look what happens. We start out with 0.1 molar C4H9Cl, and every 50 seconds we take a reading, and you can see that reading decrease, 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 decrease until at 10,800 seconds we have 0. And that's when we stop collecting our data. So let's take a look at the data in more detail in the slides ahead. The analysis involves calculating the time interval between measurements, or delta T, and the change in concentration between those same time measurements, or delta concentration of, in this case, the reactant C4H9Cl. So let's take a look at this. What is the time interval between measurement 1 and measurement 2? The delta, the change, is just the time here, 50 minus 0, so 50 seconds. In every case, right, we can do that. 100 minus 50 is 50. 150 minus 100 is 50. 200 minus 150 is 50. 300 minus 200 is 100, and this continues, okay? We can find the delta T. Now, we also have to find the delta concentration, the change in concentration. So 0.0905 minus 0.1000 is negative 0.0095, and we'll talk about that in just a second. But we can continue that as we go to continue to get our change in concentration as time moves on. Okay? Now, once we have those two numbers are divided to determine the rate. So remember that the rate is the change in concentration divided by the change in time. Okay, so I can divide delta concentration over delta T to get a rate. The rate, this is important because I have this negative here, which would make all of these rates negative. But the rate is the absolute value of the change in concentration over time. So it's always positive. Okay, the rates here are all given times 10 to the minus 4 molarity per second. Okay, 10 to the minus 4 molarity per second, just so the graph is easier to read, or the data, excuse me, is easier to read since the numbers are so small. So the rate here, this 0.0095 divided by 50 is 1.90 times 10 to the minus 4, and so on and so forth. You can see the rate decreasing with respect to time as the amount of the reactant decreases. That's important. We're going to look at that on a graph in just a second here. The rate slows as time elapses until finally reaching 0 when there's no remaining reactant. So you can see that happen these diminishing values for average rate can be seen in this rightmost column, just decreasing with respect to time. This is because as the reaction goes forward, there are fewer collisions because the concentration of the reactant is decreasing, and therefore fewer reactions. Reaction rate is like speed, where speed is measured in distance traveled per unit time. Reaction rate is measured in molarity change per unit time. So we can see our rate as the change in molarity, capital M, over the change in time measured in seconds. So this is what we use. This equation here is what's used to calculate this column in our data analysis. Okay, so what we've done in this slide is we've plotted that data from the previous slides, that experimental data with concentration of C4CHCl on the y-axis versus time on the x-axis. And it yields this curve that you see in this reddish-orange color. Okay. The slope of a line tangent to the curve at any point is the instantaneous rate of the reaction at that time. I've drawn two lines tangent to this curve. Tangent to the curve just means touching the curve at any one point. So the slope of the curve is steeper. This blue line is much steeper earlier in the reaction. And as time moves forward, the slope of a line tangent to the curve becomes less steep later on. All reactions slow down over time as the concentration of the reactants decrease. Therefore, the best indicator of the rate of a reaction is the instantaneous rate near the beginning of the reaction. So you see this blue line here, tangent line here, is drawn as close to time zero, the beginning of the reaction, as possible. And the slope of this line, the change in concentration over the change in time, is what we'll use to determine the rate of a reaction. Before we move on to any calculations or quantitative analysis, we need to talk a little bit about reaction rates and how reaction stoichiometry affects them. So we've been looking at this reaction of C4H9Cl aqueous with liquid water produces C4H9OH and HCl. In this reaction, the ratio of this reactant, the C4H9Cl, to this product C4H9OH is 1:1. What that means is the rate that the reactant disappears is the same as the rate that the product appears. So the rate is equal to the change in concentration of the reactant over time, but that is the same rate as the change in the concentration of the product over time. Now I have a minus sign here on this first one. Why? Because this concentration is a reactant, and that concentration is decreasing with time. That's a reduction in concentration. It is placed in front of the concentration of reactants since they are consumed. The concentration of products is increasing, so they don't have a minus symbol. But the value of this rate, not the negative sign, but the absolute value of this rate, is the same as the rate of the appearance of the product. What if the ratio is not 1:1? So let's take a look at this next reaction where we have 2HI gas decomposes into H2 gas and iodine I2 gas. For every 1 mole of H2 or I2 that is produced, 2 moles of HI must be consumed or must decompose. So the rate of disappearance of HI will happen twice as fast as the appearance of either I2 or H2. So how does this look in our rate equation? rate equals minus 1 over 2 concentration of HI, change in concentration of HI over change in time, which will equal to the change in concentration of I2 over time. The minus symbol again indicates the disappearance placed in front of the reactants. The products are increasing or appearing, so they don't have the minus sign. So what did we do here? We put the coefficient down here below in the denominator, in the bottom of the fraction, right? To indicate that the rate of that disappearance will happen twice as fast as that of the products. Usually, questions relate to the rate with respect to a particular reactant or product. Sometimes a question may refer to the overall rate of a reaction. When the coefficient is 1, the rate with respect to that reactant or product will be equal to the rate of the reaction. If the coefficient of a reactant is 2, for instance, the magnitude of the rate with respect to that reactant would be twice the rate of the reaction. In general, the rate of reaction is equal to the rate of any particular reactant or product divided by its coefficient. All right, so let's look at how we can write these rates for a generic reaction. If I have reactants A, capital A, and capital B, with coefficients lowercase a and lowercase b, that produce product C, and capital D, with coefficients lowercase c and lowercase d, the relationship between rate of reaction and the rate of, with respect to a particular reactant or product, would be as follows. The rate for the reaction is equal to negative 1 over this coefficient for reactant A times the change in concentration of A with respect to time. And then we just repeat that for reactant B, again with the negative sign. And it'll also be equal to product C and product D. So the thing to note is the coefficient will go in the front at the bottom of the fraction for whatever that reactant or product is. And by convention, the reactants have a negative sign as their concentrations are decreasing, and the products have a positive sign as their concentrations are increasing. But remember that the definition of the overall rate ought to be positive. We're talking about the absolute value, okay? Let's look at example 1 with reaction rates. We have 2 NO2 gas producing 2 N2 gas plus O2 gas. Now, the first thing we always have to check and make sure is that the reaction is balanced. We've been given a balanced reaction in this case, but just something to always keep in mind. As this reaction proceeded, the concentration of N2O, this reactant, dropped from 0.825 molar, that was our initial concentration, to 0.785 molar, our final concentration, in 5 seconds. There are 2 parts here. First, find the rate of the reaction, and then find the rate of the formation of N2 gas, one of the products. We'll answer each part separately in the next slides. All right, so in part A of this first reaction, we're asked to determine the rate of the reaction. And let's just keep in mind what information we've been given. We've been given the initial amount, the final amount, or the final concentration, not amount. Initial concentration, final concentration, and the time that elapsed. And I also just want to circle or highlight for a second, we're talking about this N2O reactant. Okay, so rate of reaction is given as minus, because it's a reactant, right? 1 over A, and just as a reminder, A is the stoichiometric coefficient for, in this case, N2O, so that reactant. So it's minus 1 over A times the change in concentration of N2O over the change in time. Okay? So now we substitute minus 1 over, in this case, A is 2. Okay? And then we have the final amount. Calculating change is always final amount minus initial amount. So 0.785 minus 0.825 divided by the change in time, or the time elapsed, which is 5 seconds. Okay? And after calculating that, or performing that calculation, we get that the rate of the reaction is equal to 8.0 times 10 to the minus third molarity per second. So keeping in mind that these are units of concentration on the top, so these are units of molarity, and this is unit of time on the bottom, so second, which is how we get molarity per second. Okay? So let's just analyze what this means real quick here. So the value here, 8.0 times 10 to the minus third meters molarity, per second, represents the rate of the reaction, the overall rate of the reaction. Reaction rate is always a positive number. To find the rate of disappearance of N2O, so the rate of that the N2O disappears or reacts in this case, multiply the reaction rate by -2. Because again, it's a reactant, which we get that negative. So we have negative 1.6 times 10 to the minus 2 molarity per second. The negative sign here indicates that the concentration is decreasing at a rate of 1.6 times 10 to the minus 2 molarity per second. All right, in part B here, we're asked to find the rate of formation of N2. So we'll use our answer from part A, but in this case, we're looking for the rate of formation of N2. So again, if I'm looking just at that product, rate is equal to 1 over 2. Now, where does this 2 come from? Again, it's the stoichiometric coefficient times the change in concentration of N2 over change in time. And again, this rate is positive. This value is positive because we're talking about the appearance of the product. So the value found in part A is used for the rate. So you can see that I've substituted that 8.0 times 10 to the minus third molarity per second, and then equals 1 over 2 delta N2 over delta T. And then we can solve for this rate. Okay, this right here is the rate of formation, or the rate of appearance, this change in concentration with respect to time. So all we do is multiply by 2, because we have a 1/2 here, multiply by 2. 2 times 8 times 10 to the minus third is 1.6 times 10 to the minus 2 molarity per second. This value represents the rate at which the concentration of N2 is increasing.